definition of Kepler's third law, the elliptic motion period is given as ratio of the total area of the ellipse to the rate at which the area is swept. So the rate of area can be written as dA divided by dt, and the area of an ellipse is pi AB. So if we replace this area with pi AB and the area as dA by dt, we can simply write down the equation as pi AB divided by half r into r d theta by dt. So how do we get this this part? Because this is dt, so this is dt, fine. What is dA? This is the area. So if we are basically concentrating on this particular image, and if we consider this as the radius vector, and this is a very small area swept out, which is d theta, okay, and then this part would be nothing but r d theta. So this part is r d theta. So that means dA would be half base into altitude. Base is nothing but r, and altitude is r d theta. So it is half r into r d theta, and then divided by dt, because there is a by dt here. So that's why it is dA by dt, which is half r square d theta. From the derivation of Lagrangian, we have theta dot is equal to L divided by mr square. Okay, we will look at into it again. It's a revision, whatever I'm saying right now. Okay, so we have got theta dot is L by mr square, and then it can be replaced here. This is L by 2m. So simply we can write down the equation tau is equal to 2 pi mab divided by L. The second law, or the third law, states that tau square is proportional to a cubed. So on the right hand side we do have an a, but we also have a b. So that means this b needs to be written in terms of a. Okay, so if we just write down the eccentricity equation for an ellipse, this is the equation, and if we take this equation and simplify it, we write down b as a root over 1 minus epsilon square. So if we replace it, we get the equation as this. So b, we are replacing it as a root over 1 minus epsilon square. We get this term. We can square on both sides and we say this, but then it is still a to the power 4 and not a cubed. So we're going to see this now. Now this derivation of b is equal to a root over 1 minus epsilon square. Okay, I'm not going to explain this now, but then this comes from basic maths. If you're watching it on YouTube, you can always pause it and then see. So I'm scrolling it down slowly, and you can pause and check. Okay, but then I think if we go into the final relation of an elliptical equation, we know that it is nothing but x square by a square plus y square by b square is equal to 1. And if we just look into the derivation, we can write down b in terms of a in this form, and the derivation is there, and a is this, b is this. Okay, so let's proceed from here. So we have got equation 13. We have got equation 13 as this: a is equal to p divided by 1 minus epsilon square. So a is equal to p divided by 1 minus epsilon square. We replace this p. So p can be written as L square divided by mk into 1 minus epsilon square. The question is why I am doing this? Because when we are deriving proportional to a cube term, we actually stopped at this particular point. Let's go back here. This particular point, 1 minus epsilon square. So obviously, if we just look it from pure mathematical point of view, we want to write down this 1 by epsilon square in terms of a, and that is why we are taking so much trouble. Okay, so if we write down this, we take equation 13, okay, which is a is equal to 1 p divided by 1 minus epsilon square, and p we have already seen is L, okay, which is nothing but in terms of L is L square by mk. When we replace it, we get, just do the cross multiplication, we get 1 minus epsilon square is equal to L square divided by mka. So now we can replace it in that original equation. Okay, so equation 12, it was this into 1 minus epsilon square. So if we replace this 1 minus epsilon square here and we do our cancellation, we see that a gets cancelled, a to the power 4 becomes a cube because 1 gets cancelled, m square becomes m, k remains, and k is a constant, so that's fine for me, right? So we do have 4 pi square into m divided by k into a cubed. So this tau square is proportional to a cubed. So this is the proof. Okay, So here also again we did take help from relation of angular momentum. And if you remember the derivation which you might have done in your lower class for this, there also you do take a similar approach. Okay, but here we have taken Lagrangian, but in the derivation for the third law we have not explicitly mentioned anything about Lagrangian. We have just taken the equation because we have already done it before, but then we are just using Lagrangian to find out and prove the same law which you also might have done. Okay, but then please remember, this happened to me in your previous batch. I did give a proof for proving the second law or the first law, and one of the student used whatever he or she has done in her degree. Okay, so not that's not the approach, because we are studying a different topic altogether, so we have to stick to the syllabus. Okay, so if I ask you prove Kepler's second law, and I understand that I should mention using the Lagrangian idea, even if I don't mention, it is implied that whatever has been taught in the syllabus. Okay, so sometimes I do make that mistake. So, but then you have to understand that whatever I have taught, that approach has to be taken. So this is the Kepler's third law. So what does Kepler's third law tell me? That the square of the period of elliptic motion is proportional to the cube of the semi-major axis and is independent of the minor axis. So you see this time period is independent of the minor axis. We can make it independent, okay, if we just write it down in terms of p. So this is the proof for the Kepler's third law, okay, and I think that is important. And then you might have come across a number of times this lab frame and center of mass frame. In the next class, that's on Monday, probably not on Monday, because Monday I'm going to take a quiz. So next class, it will be on Wednesday if we go as per routine. We will look into the difference of these two from a very simplistic point of view. Okay, we won't get confused. What do you mean by lab frame? What do you mean by center of mass frame? Okay, this is important because we are also going to learn about relativity, so this will work out. Okay, so I think this is clear. Okay, and that's just for the sake of YouTube recording. Okay, those who are watching it on YouTube, maybe my students or others, I do have an okay audience on YouTube. Less people are subscribing to physics, but let's see anyway. Might be 10 years down the line, I'll have more subscribers. So I was explaining second law to the class, and then all of you we can just revise it, okay, for exam purpose directly. Second law says that the area swept out in a time interval is constant, okay. So at different times, if you're considering two time intervals which are equal, okay, let's say 5 hours at this particular position and 5 hours here, both of them will equally swap out similar area, same area. That is what the second law is all about. We are going to prove that law. So for that, again, we are going to concentrate the Lagrangian, okay? All of us just revise this part. And then we are going to use the fact that theta is a cyclic coordinate and put it in the Lagrange's equation of motion. So if you put it in the Lagrange's equation of motion of d dt of del L del theta dot minus del L del theta, we get d dt of m r square theta dot is equal to 0. Okay, and of course we can put one more equation of d dt of d dt of del L del r dot minus del L del r is equal to 0. If we do that, we get this equation. So this is something which you have done in the last lecture of unit 2. So these 6 and 7 are the equation of motion of the particle, and then we have got d dt of half m r square theta dot is equal to 0. Having d dt of m r square theta dot, where m is a constant for the system, is similar to an equation like half r square theta dot. So if m r square theta dot is 0, d dt of that, then d dt of half r square theta dot is also equal to 0. So d dt of something is 0, that something is constant, so that means half r square theta dot is constant. And then the area, if we consider this diagram, is nothing but, if you consider the area here t and time t, and this is, let's say, time t dash, and this angle separation is nothing but a very small distance d theta. This can be considered almost to be a straight line, so this perpendicular is r d theta. So half base into altitude, so half base is r into altitude if you refer to this diagram. So the area is half r square d theta. So dA dt will be half r square d theta by dt, or half r square theta dot. But then from the Lagrange's second equation of motion, we can see that half r square theta dot d dt of that is 0. That means half r square theta dot is a constant. But from here, what is half r square theta dot? dA by dt. So half r square theta dot is constant. That means the area swept out is constant. The rate at which the area swept out by the radius vector is constant is the statement for the Kepler's second law. One more point we need to remember that this dA dt, the rate at which the area is changing, is also known as areal velocity. So if a question is asked on what show that the areal velocity remains constant for a planet revolving around the sun, the derivation is the same. That's your Kepler's second law. Okay? And it's important that this is true for any central force because we did not use the relation F is equal to minus k by r square or V is equal to minus of k by r, not used. If they are not used, it means that it is independent of what form the force has. Is it an inverse square law? Is it directly dependent on? It does not depend on that. So this is true for any central force problem.